All right, so before starting, any other questions? No questions? Okay. So today is actually one of my favorite topics actually. And this is the physical layer because I think especially those days not many software engineers understand the physical layer very good, right? We focus on the application development and sometimes we forget about this layer, but in fact if you know how it works, it is way easier to put your mind into, let's say, if I don't have enough traffic availability, what's happening, if the internet or the connection is too slow, what is actually happening, how the data actually gets transported from one device to another in the most bottom level. So if you understand that, you can really build from there, okay, and this will help for your understanding on how computer systems work, okay, and how data gets transmitted from one place to another. But let's jump straight into it. And we're gonna start really from the very basics. Okay, so today we're going to firstly start talking about signals. Okay, what are the different types of signals? How are those signals related to software engineering? Why we care about those? How are they related with transmitting information? We're gonna explore what is bandwidth, what is wavelength, why we need those parameters when we're creating networks and when we're creating programs. Okay, what is the connection? How the software systems actually get connected to the physical aspect of signal transportation. Okay, so that's why I'm saying it's very interesting. So firstly, we're going to start by showing you exactly the same graph that we saw last time, but this time we're going to think about communication over the network in terms of physical layer. Okay, so last time we were talking about the application layer. So if you remember, in the application layer we're having logical connection from the source and the destination, right? So you saw one line straight from here to here. With the physical layer it's not like this. With the physical layer you really care about what's happening hop to hop. Hop is either a host or a networking device like router, switch, and so on. So you can imagine the physical connection as a link, or we can say a cable, let's say, even we can use air, where the actual message in bytes gets transferred. But wait a second, so bytes, how we're transferring bytes? We don't just create numbers and shoot them from one place to another, right? It doesn't work like this. So we need to find ways to change those bytes, which are numbers, into another form that is understood by nature and that can be transported by nature. So this form is signals. Okay, a signal is what? Electromagnetic wave is a signal. Light is also a signal. Actually, the light is type of electromagnetic wave. Okay, so we can find ways to translate those numbers into signals using some specific rules, then transport those signals, and on the other side we can have a device that takes the signal and based on some specific parameters with this signal is actually reading the message and transfers this signal again to bytes. Okay, so this is what's happening in the most bottom level of our communication. So we're going to talk specifically about this. All right. So before jumping into more complex topics, we have to start obviously from the very basics. What are the different types of signals? So there are two main types, and those are analog and digital signals. So analog signals are continuous. Okay, so as you can see, they move in a way that is continuous. So for example, you can imagine this as a clock, right? So if we see the clock over there, the hands of the clock are moving continuously, not by steps. Okay, they move from left to right. But if you see a digital clock, you go, let's say, from 9:30 to 9:31. So you're gonna go in a step. Okay, It's not going to move continuous. So analog signal moves continuously, while the digital signal moves in steps. Okay? So with digital signals, it is very easy to represent bits, obviously, because here this can be 1 bit, this can be 0, this can be 1, 0, okay, this can be again 0, and so on. So we can represent bits easier, in an easy way, with digital signal. Okay. So the next thing that we need to know about signals before exploring them in details is that we can separate them in periodic and non-periodic signals. Periodic is a signal that repeats wherever it did multiple times after a certain period of time. Okay? And non-periodic is moving completely randomly. So a non-periodic signal would be when I'm speaking to you. So if I record my voice, you would see a wave like this, right? It's just gonna move like up and down in a random way depending on what I say. I cannot use the same intonation or reproduce the same exact notes in the same way. So this signal is going to be non-periodic. Okay? A periodic signal can be, as I said, a signal that represents itself constantly. Like for example, let's say if there is an alarm, okay, the signal from this alarm is always going to be the same wave. And you will see how that works. So the first thing we're going to talk about is the most simple form of wave, and this is the sine wave. Okay, so now we're talking about periodic, so signals that repeat themselves, analog, signals that are continuous. Okay, so the sine wave is a perfect example of periodic analog signal. Why? Because it just repeats itself, right? It's a wave. The sine wave has a few parameters that we care about. Those are called the properties of the signal. This is the amplitude, the frequency, and the period of the signal. With a sine wave, as I said, you can send a signal and a single message. For example, if we talk over the phone and I send you a single sine wave, you're gonna hear just bzz, that's it. Okay? You can send a single piece of information because the properties of the sine wave are repeating themselves constantly. So for example, the amplitude, which is the distance from the time axis to the top of the signal, okay, is always going to be the same and it will repeat, right? Then, do you know what is a frequency of a signal, for example? Oh, okay, very close, very close. So when we complete one revolution like this, okay, the time that it takes, this is the period, okay, which is also a very important property. Yes, so let's go to the next slide, and it's gonna be more clear, yes. So yeah, actually the period and the frequency are very much related, okay? So the period is exactly the time that it takes, okay, to complete one period, right? So one going up and down before the signal repeats itself again. So the time that we need for one complete repetition is the period, okay? The frequency is the number of periods for 1 second, okay? So if the signal repeats itself 6 times for 1 second, then the frequency is 6 hertz, okay? So this is why I'm saying they are related. So, for example, as you can see, the period is equal to 1 divided by the frequency, right? And then the frequency is equal to 1 divided by the period. So let's say if our frequency is 6 hertz, why 1 divided by 6 is going to give the period, because the period is 1/6 of a second that the signal repeats, okay? So based on those 3 characteristics, amplitude, period, and frequency, we can modify the signals so we can transport information, okay? and I'll show you how this is done. So let's move on a little bit. Okay, so now we know the base characteristics, but there are two additional characteristics that are important to talk about when we talk about signal. So we have phase. The phase of a wave is the way it starts from the zero axis. Okay, so let's say if the signal starts from zero, from amplitude equal to zero, okay, and the first revolution is going up, we can say that the phase is 0 degrees. The signal starts with increasing amplitude, and it starts from amplitude equal to 0. Okay? If the signal starts from the peak amplitude, we can say the signal starts from the peak amplitude. Okay? At point 0, it reduces the amplitude, right? And also the phase is 1/4 of the complete period. So it's 90 degrees, right? And so on. If it starts right from the middle of the period, it's going to be starting from 180 degrees, decreasing amplitude, and here it's amplitude of 0. Okay, so this is the phase. The phase is how the signal starts from the beginning of time. Now, another very interesting aspect of the signal is the wavelength. Okay, so why do we need wavelength? We need wavelength to understand how quickly a signal can travel through a medium. Okay, so even if we send signal, it is also important through what environment we send it, right? So for example, if I have a signal that is a light and I send it through our atmosphere, through air, obviously it's not going to get delivered as fast as if I send it in space, because in space it's a completely different environment. Okay, so that's why we need wavelength, and the wavelength is equal to the propagation speed, which, for example, the speed of a signal in the universe is the speed of light. Okay, so the propagation speed multiplied by the period. So we want to find out what distance one period is going to pass. Okay, so the propagation speed, okay, is, let's say, meters per second. We multiply this by seconds, and we get meters. Okay, obviously with signals, the wavelength is normally in micrometers. So how much space one period can cross in certain medium. Okay, so there is one example here. Okay, so for example, let's say in vacuum, the propagated speed of light is 3 multiplied to 10 to the 8 meters per second. Okay, and obviously the speed is lower in a cable. So the wavelength, as I said, is measured in micrometers. And here with this equation, we're going to estimate the wavelength of the red light, okay, that is passing through air. Okay, so when we know that the frequency, okay, so the frequency is the periods per 1 second. So the red light repeats itself, repeats its period 10 to the 14 multiplied by 4 times for every second. Okay, and if we want to measure the wavelength, if this travels with the speed of light in the space, okay, we're just going to divide the speed of light by the wavelength, and I'm going to get 0.75 micrometers is the distance that one period of the red light can travel through space. Okay. Okay. So obviously we cannot use just a sine wave when we transport information, correct? We cannot it's completely useless when we want to transport a big amount of information. For that reason, we will need to use composite signals, okay, or signals that are created from multiple sine waves. But as you can see here, with this type of graph, I can I can display one sine wave and it repeats itself. But if I want to display, let's say, 5 or 10 sine waves, this graph will be very crowded. So you're just going to see a lot of waves. For this reason, we can use another graph that is called frequency graph, or the frequency domain. Here, you can represent every signal by amplitude and frequency. So, for example, if the frequency of a signal is 6, like this signal, okay, we can represent it by creating a dot right here, and if the amplitude is equal to 5, this bar will represent a signal with frequency of 6 and amplitude of 5. Okay? Here I'm writing 5 volts because this is an example of electric signal. So the amplitude of electric signal, we measure it in volts, and this is how you can actually display it. All right. Okay, so you can see in this example right here, in this situation, if we have 3 signals with different amplitude and frequency, instead of having this type of graph, which is way more complicated, this one has, so this signal, what frequency it has? This one right here. What do you think, guys? Any ideas? So this signal, the black line, what is the frequency of this signal? What do you think? So the frequency of a signal is how many times it repeats itself for 1 second. And this is 1 second, right? So this signal, how many times it repeats a pattern for 1 second? Since it's a straight line. How many? It is actually 0. Okay? So infinite would be if it would go up to infinite and down to infinite for infinitely short time. Okay? Then we'll have infinite. Okay? But in that case, it's going to be 0. Okay? So it is going to be a spike right here since the amplitude is 15. Okay? So this one right here, how many times it repeats itself for 1 second? So there is 1, 2, 3, 4, 5, 6, 7, 8 times. Okay, so the frequency is 8. Okay, and the amplitude of this signal is going to be 10, right? So, or we should say the peak amplitude, right? It's 10. So, for that reason, we have it right here at 8 and then 10. And this is how you can see that it's way easier to represent multiple signals by the frequency domain. All right. So, as I said, a single sine wave is very difficult to use it for data communications, right? So, in the actual communications, instead we're using waves that are way more complex. Okay? So we're going to use waves that are looking like this. Okay, so that type of wave can be broken down into multiple sine waves, which means, let's say, if we can break this composite signal into 3 sine waves, this means we can send 3 pieces of information. Okay, just with 1 wave. And in real life, you have thousands and thousands of sine wave that are building a single signal. Okay? So how that happens? Now, if we imagine this wave, we can decompose it into 3 waves. So first of all, the first sine wave will be this one right here. Okay? This is our first sine wave. Okay? We can represent it like this. Then we have our second component of the composite signal, which is this one right here. Okay? So this sine wave, we can represent it right here with this one. And finally, we cannot see that, but let's say when we have this signal, right, instead of just going here like this down, it can actually go down like this, see? Okay. So there is another sine wave right here. And we can go on and on and on and on multiple times. Okay, so there is a third sine wave that is right there. So normally the main sine wave, the one that has the lowest frequency, is called the harmonic. Okay? Then the one that has, let's say, 3 times higher frequency is called the third harmonic, and the one that has 9 times the frequency is called the ninth harmonic of the wave. Okay? So you can imagine if you want to transport a message with analog signal, okay, you're gonna create a very complex wave that is composing of multiple signals, and every single is going to represent, for example, some bits, right? You can do that. Alright, so now we already talked about composite signals, okay, that are representing perfect sine waves, right? And we show them how they're displayed as just spikes on the frequency domain. So when we have a signal that is composite but it doesn't repeat itself over a period of time, then we can decompose this signal. So for example, let's say this is a signal that comes from the human voice when we speak, okay? We get something like this. So here you can see that there may be thousands and thousands of sine waves, because every small variation here it's an example of different signal, okay, of different sine wave. So I can make one sine wave out of this part, I can make one of this part, and so on. It's gonna be so many of those, infinite number. Okay? And for this reason, if I want to represent the signals that compose this one, okay, I will just represent this as a waved line right here. So if you look very closely, here is going to be one of the composite signals with its specified frequency and amplitude. Here is going to be another one, a third one, and so on. So what that means, we cannot really find how many signals are building this composite signal, okay? But what we can find is which signal has the highest amplitude and which signal has the highest and the lowest frequency, right? So we can pretty much find the range. Let's say if we have a composite signal, we can say, okay, this composite signal has multiple signals inside that start with frequency from 0 to 4 Hertz and has amplitude from 0 to wherever is the maximum amplitude, okay? So we can find this, although we don't know how many signals there are. And we can draw all of them like this, okay? Now, this is very important. I'm not just showing you those things for no reason. And you will see why. Okay. So, have you heard about bandwidth, right? This is something that is very important when we're connecting to a network. We want to have as higher bandwidth as possible, right? This is important. The more bandwidth we have, the better. But what is actually the bandwidth? Well, the bandwidth is the range of frequencies a signal has. So the more sine waves are consistent within a signal, the higher bandwidth a signal has. Okay, so what is that? Now, let's say if I have a periodic signal, so signal that consists of multiple sine waves, and let's say I draw the frequency and the amplitude of each signal. So this represents each signal that builds my composite signal, right? So I build those spikes right here. The bandwidth will be when I subtract from the signal with maximum frequency the signal with the minimum frequency, okay? And this will mean that if the signal with minimum frequency has frequency of 1000 Hertz and the maximum frequency of a signal is 5000 Hertz, our bandwidth will be 5000 minus 1000, 4000 Hertz, okay? So this would mean that every frequency right here or every wave can represent some information. So the more bandwidth we have, the more bandwidth we have, the more signals are composing our composite signal, the more information we can send. That's why if you have more bandwidth, you can send more information, more traffic can be exchanged. If you have less bandwidth, less information can be exchanged. Okay? With the non-periodic signals, it's the same. So obviously there we don't know how many signals are composing a non-periodic signal, but we know the one with the highest frequency and the one with the lowest. So again, we can subtract those and get the bandwidth. Any questions so far? All right, so here is an example of how you can find the bandwidth. Let's say we have a periodic signal that is decomposed in 5 sine waves. Okay, you can see the sine waves. And obviously you can see that all of them, they have the same amplitude, but they have different frequency, right? So the frequencies of the signals are 100, 300, 500, 700, and 900. What is the bandwidth of the signal, of the composite signal? So you can see that the bandwidth obviously is going to be the highest frequency minus the lowest, and it's going to give you the bandwidth in hertz. So those types of tasks I might also give you on the quiz, okay? So it's a very easy one. This is like first grade math, but of course you need to understand exactly what and how to calculate, right? You need to know. All right, and you can also do it the other way around. Let's say if I have the bandwidth of a signal, okay, and I have the highest frequency, obviously I can find the lowest one. So I'm just going to do the highest minus the bandwidth is going to be the lowest. All right, so now once you know what are analog signals, now let's talk about digital signals. Okay, so with digital signals, now we can start incorporating bits. Okay, so this is a typical digital signal. So if the digital signal is basically moving in steps, okay, that are that can be repeated or not. So it's very rare that we have periodic digital signals. Normally we have non-periodic. So the digital signals normally they don't repeat themselves when we use them. So let's say if we have a digital signal that has only 2 levels, okay, so it just goes up and down like this, okay, we can represent 2 levels. Actually, I'm going to ask you, with how many bits we can represent 2 levels? How many? 8? Okay. 2? Okay, any other suggestions? What do you think? How many bits we need to represent 2 levels? 3? How many? 4? Okay. How many bits do we need to represent 2 levels?
8.
8? Okay. What do you think? 8? Okay. We need 1. But good try. Actually, I think I did the same thing with when I was talking to you about the pixels in the pictures. If it's black and white, how many bits do you need? Well, if you have 2 options, obviously you need only 1 bit, right? So 0 will be this level, 1 will be this level. So you need 1 bit that can be shifted from 0 and 1. Okay? Makes sense. Now, I know that some of you saw 8 bits over there, so you thought, oh, maybe it's 8 bits, right? But it's not exactly like this. So now, if we have 4 levels, how many bits we need to represent 4 levels? 2 bits. Nice. Good one. Good job. Yes, exactly. We need 2 bits to represent 4 levels. So obviously, the more levels we have, the more bits we need. Okay? So if we have a signal that consists of 2 levels, okay, and the levels are changing, okay, within a certain amount of time, then we can actually see how many times the signal changes within 1 second, right? Okay, and every change, like for example here, 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 we keep the same one, here, 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 we can see how many times it changes, and we can see how many times it changes for 1 second, right? Okay. So with every change, we are going to transport information. We're going to transport 1 bit. So the amounts of change we're doing for 1 second in 2-level signal is also the amount of bits we're sending for 1 second. So we sent 8 bits, right? Because each change is denoted with 1 bit. If we have 4 levels of this signal, obviously, since for each change we're using 2 bits, this means we can send 16 bits for 1 second. Okay? And this is where it comes the bits per second. Okay? So, if you think about it, the more information you can send, okay, the faster internet you're going to have. Okay? So, if the signal is able to send, let's say, 1000 bits per second, obviously it's going to be able to transport more information. And this is from where the term bits per second comes, exactly from the transportation of digital signals. Okay, so let's see one interesting example. So let's say we know already that the bit rate is the number of bits that are sent for 1 second, right? So let's assume you need to design a network, okay, from where a person should be able to download a document of 100 pages in 1 second, okay? So your goal is to design a network where a document can be transferred that has 100 pages can be transferred for 1 second. So you need to find how many bits per second your network needs to support. So let's say that one page has 24 lines, every line has 80 characters, and each character normally is equal to 4 bits or 1 byte. Okay? So if you want to estimate how many bits per second you need, you're gonna multiply the number of pages by the number of lines per page, by the number of characters per line, by the number of bits per character. Okay? And this will give you 1,536,000 bits, or in order for your network to work properly, you will need to transport those bits for 1 second. Okay? So this is how you can estimate it. Okay, so now this is something I think you'll find it interesting. So if I can just send digital signals, right? Why do we even need to study analog signals? I mean, digital signals, computers already understand them, right? Because if you plug in a digital signal to a computer, it just reads the levels, it takes the bits, that's it. So if two computers need to communicate, why do I need analog signal to send this information? What could be the purpose? Not exactly. Not exactly.
Microcontroller or something like that.
Not exactly. Any other suggestions?
It's probably faster.
Faster? Not exactly. Not exactly.
Probably more secure.
More secure?
Yeah.
Actually, we're going to see how signals are getting transferred in a secure way. And we're actually, when we talk about security, we use analog signals. But the reason is different. Okay?
More accurate?
Say again?
More accurate?
More accurate? No, no. They are both in the same way accurate. I mean, in the analog signal, the information is transmitted.
Speed also will be the same.
Same. So just to mention, with analog signal, we are measuring we're finding the message by measuring the amplitude in the period, right? So this is also very accurate. Okay, so it is not that as well. Okay, so we're going to talk about this. No worries. Now, I will show you two ways to transmit signals. So one of them is if we don't use analog signals, and the other one is if we use analog signals. Okay, and you're gonna see the advantage. So if we don't use the analog signal, we're going to transmit just the digital signal, let's say between two computers. Okay? So when we transmit a digital signal, the bandwidth, okay, or the bits, so with the digital signals, we can measure the bandwidth by bits per second, how many bits can be transferred, okay? So the more bits can be transferred, the higher bandwidth we have, we can transmit more information, okay? While with the analog signal, the more range of frequencies we have, the more information we can transfer, and this is the bandwidth of analog signal. So with digital signal, always when we transfer bits, we have the bits from 0, let's say to 1000, right? We cannot have the bits from 100 to 1000. It's impossible. We always have from 0 until the amount of number of bits we want to transfer, correct? Okay, so this means that always our bandwidth will start from 0 until certain position, right? Until certain amount of bandwidth we have. So that's okay. Let's say two computers want to communicate with each other. They create a link between themselves and they exchange information like this. That's fine. But what happens if another third or fourth device want to use the same link to share, to also exchange information? Well, this other device will also have signal that starts with bandwidth from 0 until some position, right? So this means that if multiple devices use the same link, the bandwidth is going to overlap, okay? So if I send a message from two devices, the first bits that are covering the overlapping range are going to get, we're going to get confused where we have to deliver them, which bit means what, and so on. This in the same way, let's say if I talk and you talk at the same time, okay, we both produce, in this case it will be analog waves, but they are going to start from the same frequency because the human voice has the range of frequencies from 0 to 4 kilohertz, okay? So when I start speaking and you start speaking, if somebody is listening to us, they will not know what information is coming from where, and you're not going to hear anything, right? It's going to be more difficult for you to hear. Okay, so, and also when we're speaking, we're using again the same link. We use the air around us, okay? So for this reason, we need to be able to separate the signals from each other, okay? We need to modulate them. And this is only possible with analog signals, okay? So I can say, so if I pass a signal, I take a digital signal and modulate it, okay? So I will show you how this is done. But if I transmit this digital signal to analog, okay, and I increase the frequencies of the analog signal, then I can move the bandwidth wherever I want, okay? So let's say if I speak to you, right, and I use analog signal to transmit my voice, and I shift it, so I increase the frequency of my voice, not from 0 to 4, but from 8 to 12 kilohertz, then our voices will be completely separated and there will not be problem for us to transmit the information. Okay, so for that reason, you need to convert the digital signals into analog in order to be able to use the same link to share information. Okay, and I will show you how this is done in a second. Okay, so let's say we want to transport a digital signal, right? And I want to create an analog signal out of it. So what I'm going to do, I'm going to pass it right here to a device that is going to add some analog signal. And where my digital signal has a step, I will simply increase the amplitude, okay? When the step goes down, I will reduce the amplitude, okay? That way, I will mimic my digital signal with analog one. If there are two digital signals that are looking exactly the same, it's just for the other signal, I'm going to use different amplitudes. So for the other signal, I can use higher amplitude, okay, in all the directions. So they're not going to overlap. Okay, that way I will be able to transmit multiple signals in the same link. So then I will transmit it to the link, and when they arrive, of course, here we're gonna have analog to digital converter, and it will find out based on the amplitude in this case what the exact digital signal is. All right, so I know that this was a little bit complicated, right? Especially when you hear it for the first time. So for this reason, let's step a little bit back. We're going to talk about the performance of the physical layer. And after that, I will show you different techniques for digital to analog modulation, which are very simple. All right. So we can measure the quality of any link by those two parameters, throughput and latency. Okay? So let's say if I want to deliver a message and this message is passing multiple physical layers, right? So it passes multiple routers, and between every router and between me and the first router, there is a different physical layer, which means there is different type of cable that has different type of capacity, different type of bandwidth, okay? So the throughput of a network is measured by how many megabits are in fact transferred at the destination, okay? So let's say if you imagine our network as a highway and the information we want to send as cars, okay? And let's say this highway has 3 lines, right? So if along the highway we have some lines that are blocked, even though here the bandwidth is going to be high, so many cars can pass, right here we have a region where not as many cars can pass. So maybe the bandwidth of certain links is going to be 1,000 cars per second or per day. But because there were regions in the network with lower bandwidth, the final throughput of our network is obviously going to be lower. Okay. So here's an example. Okay. So if you have a network with bandwidth of 10 megabits, so they can pass. Okay. But in fact, we pass on average 12,000 frames per minute, with each frame equal to 10,000 bits. What is the throughput of the network? So even though the bandwidth is 10 megabits, we can measure that only 12,000 frames with 10,000 bits each can pass. So we can multiply those, okay? For 60 seconds is going to be 2 megabits per second. Is the actual throughput of our network. And then the final thing that affects our network is the latency. Okay, so latency is normally a combination of certain delays. Okay, so normally you're having propagation time, okay, which is a time required for each bit to travel from the source to the destination. Okay. Then you have the transmission time, okay? That really depends on the bandwidth of the channel, so how much information can be transmitted, okay? And finally, the queuing time is the time that the messages might wait, or the bits might wait. For example, some routers might reach their maximum capacity, so some messages will get queued, or some bits will get queued, and this time will also be added to the latency. Okay, so when we measure the performance of a network, we're going to use the latency and the throughput, which are not necessarily dependent always on the theoretical signal passing through a medium. Okay. Yeah, we talked already about this. So obviously, if we want to pass digital data with digital signals, you can represent 0 with this level, 1 with this level, and as you can see, it is very simple. But obviously, you can use only a single link for communication between two devices. No. Okay, so we don't need to go into that. Okay, transmission modes. Okay, so when we want to transmit data, okay, sometimes we can use a parallel or we can use a serial transmission. So what those mean? Parallel means that we're shooting multiple bits at a time. Okay. How this can be done? As you can see, the signal has different level at different time, right? So how can we send bits at the same time? Well, to do that, we will need to use multiple links. Okay, so let's say if I want to send a message with parallel transmission, okay, I'm going to send every bit or sequence of bits with a different signal, and obviously the message will be delivered way faster because I will use 8 links to transmit 8 bits at the same time. And like this, so this seems pretty efficient, right? So can you tell me some disadvantages of this type of scheme? What do you think? Exactly, cost. So this is obviously going to be very expensive because for transmission between two devices we need to use 8 links, which is a lot, right? Instead we can use only 1 link. It's way cheaper, 8 times cheaper. Okay, so the digital transmission obviously can be used for some very small networks, but if you want to transport information over very large distances, we cannot do that. So the other way is serial. Okay, you probably heard about serial connection, right? So serial means we are transmitting the bits, yeah, one by one, okay, in series. So first we go on to transport 0, 1, and so on. So let's say if we want to transport 1 byte, which is 8 bits, we will transport them one after another through a line, normally a wire, or we can transport it over the air as well. Okay, so let's see some different ways of doing that. So there are 2 main ways to do it. The first one is called asynchronous, and the other one is called synchronous. Now, asynchronous transmission means that for every byte that we set, so 8 bits, okay, we don't need the sender to be synchronized with the receiver, which means that they don't need to keep track on their clocks. Even if 1 byte gets delivered before or after the other, it's not a big problem, okay, because we synchronize them. We synchronize them within itself, but the bytes that are sent randomly. So since they are sent randomly, how do we identify where a byte starts and where it ends? To do that, for every 10 bits or 1 byte, before it we add 1, and after it we add end bit, which is 0. So when those messages arrive, okay, when we get 10 bits that start with 0, we know that this is the start and then this is the end. So inside this byte, the bits are synchronized, but the bytes itself can come at different times. So can you tell me what is the disadvantage of this scheme right here? Any ideas? So obviously one disadvantage is that we add 2 extra bits to identify the start and the end of each byte. So we need to add a 0 in the beginning, so 0 at the start and 1 in the end, which means that we transport more information, so we're just wasting a little bit of our link. The second way is synchronous transmission, where the sender and the receiver needs to keep track on their clocks. So the sender, actually the receiver needs to know at what time the sender sent the information, so it can expect the information in order, okay? Because the timing here becomes very important. Okay, so in that way, the information gets transmitted in big frames of bits, and that's why we need to have synchronization between the sender and the receiver. Okay, so now there's a situation also that we need to convert an analog signal to another analog signal. And the best example of this is, for example, the radio that you listen in your car. Okay, so you can see that when you listen to radio in your car, you have different frequencies for the different stations, right? So the stations that I know are 94.5 is the one I listen, and also I listen 96.9, okay, because they put pop music and I like pop music, right? So those numbers, they mark the frequencies, actually the bandwidth, okay, the starting frequency of the station, right? So the station that is 94.5 starts at 94.5 megahertz, okay, and since the human voice is so the human voice is from 0 to 4 megahertz. When it's modulated, it becomes in kilohertz. But let's say it starts from 94.5 until let's say 95.5. Okay, so we leave around 100 megahertz for the voice. And after that, you have another station. Okay, so you're having the separation of the different stations just because we're modulating the human voice into a different analog signal. So you have amplitude modulation, frequency modulation, and phase modulation. So when we have amplitude modulation, you have the AM radio, okay? With frequency modulation, we have which radio? FM, right? We have the FM radio. And then the phase, we have the PM radio. Okay, so in amplitude modulation transmission, we are modulating the original signal based on amplitude. Okay, so what's happening? Let's say this is the original signal that the radio has, that the hosts are speaking about, right? So now, if you want to modulate it, so we want to change the range of frequencies that this signal covers, we can mix this signal with a carrier frequency. Okay, so this is the carrier signal. Okay, and as the amplitude of the original signal changes, okay, we're going to change the amplitude of the modulated signal. Okay, so finally we're going to get this. So this is going to be our modulated analog signal. When we do that, we'll need to increase the bandwidth of the original signal 2 times. Okay, so this will be the range of frequencies that the original signal covers. Okay, and you can see that, for example, for the AM radio, let's say the first station is going to be modulated, so it will start at 530 kilohertz until 540. Then we'll have some gap, some empty space, so the signals, they don't interact with each other. And then we're going to have the next station. Okay, so with the frequency modulation, it's pretty much the same thing. It's just here we change the frequency of the carrier signal based on the amplitude of the original signal. Okay, so you can see that here we have the same amplitude, but we just change the frequency. With the FM radio, we have the range of frequencies from 88 megahertz until 108, and each station is going to take around 200 kilohertz. Okay, so here will be one station. Okay, and then we'll separate them like this. So if we wouldn't do that, all the stations will start from 0 to 4 megahertz, right? And then when you receive them, the voices of the hosts for the different radio stations are going to be overlapping. Okay, and the final way is to change the phase based on the amplitude of the original signal. So here exactly the same approach. we're just changing the phase as the amplitude of the original signal changes as well. Okay? Alright guys, so that was everything for today. Next time we're going to continue, so we're going to explore next time some network devices and how they work into the physical layer. Okay, so today were just the basics on how signals work. So you have some background for our next lecture. So I advise you to read also the reference material to this one, because I know now when you hear about more physical aspects, signals and those type of things, it might sound confusing when I'm explaining them to you right now, okay? But I'm sure if you read the reference material, you're going to get better in understanding those, okay? And it is important because this is really the basics on all the devices that are the backbones of the network these days.